Hello everyone. Today is the 39th day of Leetcode 75 challenge. Let's begin with the 39th question. Question 199. Binary tree right side view. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. Suppose you are given, here in the question you are given the root of a binary tree. You are asked to imagine yourself standing on the right side of the binary tree. Okay. So let me draw a binary tree here and you're standing in the right hand side and you are looking from this direction. Fine. You're looking from this direction. Okay. Your task is to return the values of the nodes that are visible from the right side, order from top to bottom. Top to bottom is from the root node to the leaf node. At each level of the binary tree, only one node of the rightmost will be visible to you. Why? Because if you try to make some sense out of it, is that if you're standing here, then you will see only this node from the right side, correct? Then if you come to the next level and if you look at the node, this particular node is behind this particular node. Fine. So if anything is behind something, suppose this is one of the boxes, another box is just behind it, right? Our naked eyes would not be able to see it until and unless we remove this particular box from front, right? The same thing is in this particular case. Here also, if in this level also, you will just be able to see this particular node, not this one or this one, right? The final output would be list of these visible nodes starting from the left level down to the bottom of the tree. Okay. The constraints of the problems are the number of the nodes in the tree is range from 0 to 100, fine, and the node value is from negative 100 to positive 100. So basically, we just have to return all the nodes which are visible to us from the right hand side only. That's all. Or you can just say that the rightmost nodes of each level we have to return those. Fine. Now let's move to the next slide. Now let's understand the input output explanation. So this is one of the tree given, right? And if you are looking from this particular side, right? In this given example, you could see that 1 is visible, 3 is visible, 2 is not visible because it is behind this 3, right? And similarly, 5 is not visible because it is behind 4, right? That's why the answer comes out to be 1, 3, 4. Similarly, here also, if you look it from this end, you can only see 1. Then here in this case, level 2, you can only see 3. But in this case, level 2, 3, and 4, you will only print out 4 and 5. Reason being, you don't have anything in between, right? There is no obstacle or any node in between. You directly can see these two nodes, right? That's why the output for this particular comes out to be 1, 3, 4, and 5, I guess, right? Yeah, 1, 3, 4, and 5, right? So this is the thing. I hope you understood this input output explanation. This is pretty easy and it's pretty straightforward. Now let's move to the next slide. Before going to the further slides, let's understand what is breadth first search. Okay, a BFS. If you already know what is BFS, you can skip this part. Otherwise, please pay attention here. BFS is basically stands for breadth first search. Is a traversal method where we visit all nodes level by level from top to bottom and left to right. This is left to right in general case, or you could go from right to left as per the required question. Right? That's the thing. How it works. Okay. Important thing. We start. Suppose this is the binary tree. So this is one level. This is another level. Level 1, level 2, and level 3. This is clear. Okay. There is nothing much to be understand here. So how we do it? How do we do it? We start from the root node, of course. We use a queue. This is the queue. Okay. We push this particular root node here. Okay. Now what we do? We put its children uh, after that. How we do it? We dequeue a node and process it. Suppose we put one here, the root node. We popped it out, and after popping it out, we look for its left and right childrens. Left first, then right. And if any question it is required right first and left, then do it that way. Otherwise, the general form is left and right. So if we pop out one and if we go for the left node, we have 2 here, then we have 3 here. Okay. Now, if you have observed, after doing this, this was level 1, fine. Now this is level 2, correct? Then you popped out 2 also. Then you try to took 4 left and took 5 for this particular node, fine. Let me extend this. Then you try to pop out 3 also. Then you took 6 and 7. Now, if you have observed, this is level 3. So, until and unless the before level is not completely emptied from the queue, you won't be able to access the second, no, upcoming levels, correct? And every time when we pop one level, we already have been filled the queue with the upcoming level of that particular thing, or n plus one level. Correct? So this way we go level wise for in the particular given tree, and we repeat it until the queue becomes empty. And when we reach at the seventh value or the seventh node in the queue, when it gets empty, that means we have completed traverse our binary tree. Now, why is it efficient? Time complexity is O of n. Each node is visited once. That's why. Space complexity is O of W for each particular traversal, or we could say the maximum width could be O of W, right? Right. If you are storing by chance, if you are storing it in the array, okay, then it will be O of n. But in the queue, the maximum number of nodes at one time could be the maximum width we have in the particular tree. Great for finding the shortest path in unweighted graph or trees. Useful when we want to process nodes level by level. Okay, this is a simple explanation of how breadth first search works. And let me give you one more thing. Suppose you have popped out one from the queue, correct? Then you go for the length of the queue, because when you pop out one, you already have node 2 and 3 under it, right? So the length of the queue becomes 2. So which means we will traverse or we will write a for loop which will go up to 2. So this also isolates each level. Fine. Now, when you will push the child nodes for 2 and 3, the length of the queue will become 4, correct? Then we will take the length of that particular level like this, and again it will isolate, right? So this helps us to traverse in most isolate way and more easier way. Fine. Now, where we use BFS, we used to do when you want to do the level of the traversal, when you want to print or process nodes level by level. Example, print each level of a binary tree on a new line. Okay. When you want to find the minimum depth, BFS stops at the first leaf node, it's fine, correct? Then more efficient than BFS for shallow trees. Find the shortest path from root to leaf node, right? These are the ways where we can use BFS. Okay. Interconnect nodes at same level. BFS easily tracks nodes on the same levels, right? Populate next pointers in a perfect binary tree. So these are the questions you could say, or the logics you could say, where we can use BFS. Suppose in serialization and deserialization of the tree, convert a tree into a flat structure, or doing a zigzag or spiral or traversal variant of level order with direction switching each level. So these are the questions you could say, or the concepts where we use this level order traversal or BFS. BFS is also called as level order traversal because that makes much more sense to hear, right? That's all. I hope you understood this explanation of BFS and how we iterate it. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Okay, let's do that by understanding the goal. We are given a root of a binary tree. Let me draw a binary tree. Our task is to return the nodes of the, we have to return the values of the nodes that are visible from the tree, is viewed from the right hand side from top to bottom. Okay, that is clear to us. From this view, at every level of the tree, only the rightmost node is visible. That also makes sense to us. So we need a way to collect one node per level, especially that the one that would be the last visible node from the right, or basically we could say the rightmost rightmost node. Fine. So what could be the brute force way to solve it, right? A brute force way might involve collecting all nodes at each level, okay, and selecting the last one, but that can be simplified. How? Let me tell you. First of all, what is brute force tells you? Brute force tells you that you will be taking a 1D array. Whenever you go for the new level, you update this. Fine. Update at each level. So basically, when you write while queue is not empty, correct? You take the size of the queue here, right? Then you go for the for I to size, correct? In this part, you update the vector every time, fine? Or basically, you initialize the vector again. So what happens in that case? In every level, you will store the nodes here. Well, suppose 1, 2, 3, 4, 5, 6, 7. So in first level, you had one, okay, and the last node was also one here, fine. So you stored it into a vector, correct? Then in the next level, you had 2 and 3. So what you did, you just returned or you just did pop back or you just returned, let me clear this up, or you might just return, array of -1, which means basically means the last index value. So this way you could store all the nodes value in the vector, then get the last value and push it into the main vector so that you have to return the all the nodes from the rightmost part. That's why we need a vector for it, or you could say an array for it. Okay, so you could store it in there. But this will take an extra space of O of W, correct? So we have to remove this. We aim to traverse a tree level by level and directly pick the first node as we see from the right to left at each level. Okay, this lets us efficiently capture the right view without additional space or post processing. Right. To remove this particular chaos which we are doing, we're storing it in the vector, then we're pulling out the last value, then storing it again in the main array to return. So just to remove this particular space which we are using, let's do something else. Okay, let's visualize the process. We perform a level order traversal, a breadth first search, using a queue to visit nodes level by level. We know this. We know this how we do that, right? At each level, nodes are processed in a specific order. We will go from child first, then left. If you remember, I told you earlier also when we were talking about BFS. BFS is generally left to right, correct? But if the question requirement is we could start from right first, then left, correct? If you go for the right, then we will always, if you go for the right, we will always put this node first in our vector or in the queue, right? Let it be this here. Then we will put this particular node, correct? Then again, when this is done for this particular node, we will put again this particular right node, correct? Let me draw it more nicely. Let this be a queue, okay? So if you come here, you will put this particular node 1 here, correct? Then when you go for the further nodes, suppose you go for this further node, right? So for this, instead of taking left first, you took right. Okay. So what happens in queue? It becomes 5 and then 2. And 1 is done. We don't require 1 anymore. Now, then you pop this element, right? Then again you go for the right node first, which is 7. Then you go for the left node, right? Similarly, when for the 2, when you pop 2, you go for the 5 first, then you go for the 4 first. 4 seconds, right? So what happens this way? When you pop the element, this is the leftmost node. Of course, 1 is the leftmost node or the rightmost node. 1 is common in every case, right? So 1. When you pop 5, you could take 5, right? When you pop 7, you could take 7. Now, this is the one thing which is clear. Now, you might, okay. Now, why this order? Because you want to see the rightmost node first at each level. So, the first node encountered at each level is the one visible from the right side, correct? Because then, when you encounter first time the rightmost node, in this case, when you I is 0, what is this I? This is the for loop of the queue size. If you remember, we take the size of the queue for each level, right? So in this particular I equals to 0, and when you do right node right, this is the first node always. So you could directly push it into the resultant vector or resultant array, right? In this case, if you took right, right is the first for this particular level, correct? You push it. Suppose you didn't had this particular node here, okay, the rightmost, then what would have happened? It would have happened. The leftmost node would have been the answer, right? So in that case, right is not there. So you try to push left, right? Then instead of 7, it will become 6. Okay. As we loop through nodes at that level, the first node is the visible one, and we add its value to the result. If you have taken by chance, if you have taken not not I equals to 0, and also you have taken left and then right, then this condition might have been changed. It would have been I equals to n minus 1, because the last node which you pop from the queue will always become the rightmost node in that case. Okay, because the rightmost node is pushed at the last in the queue. Because when we were doing left and if you're doing left and right, so what we will do? One is popped, then we put two here, then we put five right in the queue. So this is not the rightmost node, right? And I is equals to 0 and 1. So when you come in the one part or when I equals to 1 or n-1, you have the rightmost node. But since you are taking the rightmost node first, we check I equals to 0. When we take the rightmost node, suppose we take the right first, this becomes this, and here it is 2, right? So this is 0 and comma 1, right? That's why I did I equals to 0. That is why we take the first node, which is the rightmost node. Similarly, if after this, if we try to pull, right is not there, so we put the left node, right? So it becomes 6. So when this level is done and we have some values here, so this is the zeroth part, right? Or zero starting for this particular level, right? So this is the one which we will take, right? I hope you understood this part. Children are added to the queue in the right to left order to maintain visibility priority for the next level. Fine. Now, how we can simulate this? We initialize a queue with a root node. Okay, before going to the main traversal also, while uh, queue is not empty. For before going to this traversal also, we will just put the root node in the queue. While queue is not empty, we determine the number of nodes at the current level. We do it by how? We do it by length of the queue. Okay. We'll look through these nodes one by one. Please, why we are doing this length, please try to understand. Is if you have the knowledge of BFS, it is not a big thing or big deal to understand. But if you don't have the understanding, it is just as simple as that. If you have some length, suppose 3, and this is of particular level 2, right? So this isolates this particular level so that there is not any, mishandling of the nodes. That's all. For the first node at current level, we record its value. It's the visible one from the right. Because whatever the node is there, the first node in the queue is always the visible node from the right hand side. Fine, always. Push its right, then left children to the queue so that on the next level, we again start from the right. Repeat this process level by level until the queue is empty. Right? This is all. This is the very simple thing. I hope you understood this explanation. Suppose let's take a tree. Initially in the queue, we have pushed one, right? Okay. And when you pop this one, what you do? You enter its right node and then the left node, correct? So you entered what? You entered 3, then you entered 2. This is done. This part is done now. Okay. Then you take the length of this current size of the queue or the current length of the queue, which is 2 in this case. And when you write the indexes, you write in the case of 0, comma 1. Am I correct? Yes. So this is the rightmost node here. You can see it. And I is equals to 0. We write it, right? And if I equals to 0, we just append it into our resultant answer. Okay. And we pop this. Then when we pop it, we put its right node, and since we don't have its right node, we push the left node in the queue. Correct? Then you go for the 2. When you pop it, you take the rightmost node, which is 5. Then you take 4. Correct? Then you take the length of this particular queue, the current length. It is 0, 1, and 2 in index wise. Right? Then you check I equals to 0. What is it? It is 6. When I is equals to 0, it is 6. So you put 6 here. Right? Then you do the traversal for the further leftover ones. Then you could see the output is 136. And if you check, rightmost view is 1, rightmost view is 3, rightmost view is 6. So this makes our task easier. You could also go left to right if you want, but that's all that in that case you just have to go from I equals to n-1 if you check for the last node here. Okay. So what to figure out? That the key insight is that at each level, the first node visited when traversing the right to left is the rightmost node. Okay. By modifying the traversal order and selecting the first node at each level, we directly obtain the right side view. Correct? This approach avoids extra memory or complexity. If you remember, we were trying to use extra space to store the values, and after storing the all the nodes of the particular level, we try to get the last node from it. And it's both space and time efficient while staying easy to implement. Okay, I hope you understood the intuition buildup. Now let's move to the next slide. Now, since you get the intuition of the problem, let's look into the approach, how we're gonna solve it. It starts with the step one, handle base case and initialize the data structure. Okay. First thing, base case. If the root is none, we return an empty list since there is no nodes to process. Fine. If the tree is already not given to you, nothing to be processed is there, right? So you return the empty array or empty list. Otherwise, we initialize an empty list result to store the right side view values. Suppose let list equals to this, simple. Then a queue, which is a DQ basically. Why DQ? We could do pop left, append left. If you remember in DQ, we can push it from the back, pop it from the back, and push it from the front and pop it from the front. Front is done by writing pop left and append left, and push and pop from the back is just done by pop or append. Right? This will help us to perform by using level order traversal. And why we're doing this? Because we want to visit each node of the tree and pick the rightmost node visible at that level. Now I do step two, level order traversal. We start a while loop that continues as long as the queue is not empty. Fine, that's not a big deal. Suppose this is the root road, right? And initially, before going for the traversal, you have stored this root node in the queue, right? And unless the queue is not empty, we will keep on traversing. And at the beginning of each level, what we will do, we will determine the number of nodes at that particular level, which is basically the length of the queue. Okay. And this let us isolate nodes belonging to the same level in the tree. If you remember, I discussed this thing previously also, there's the same thing. And then step three, we process each level and select the rightmost node. And this is the important one. For each node in the current level, we pop left, we pop it from the queue. Okay. If it's the node of the traversal, if I equals to 0, we add its value to the result. Suppose we pop the value and I in that case is 1, we push it into the vector. Fine. And this works because you're pushing right children before the left. So the queue always starts with the rightmost node. These things are very much clear. Okay, as we have discussed this already before. Now, when we push the node children to the queue for the next level, we have to check whether the right child and the left child exist or not. Suppose if you're standing in this particular node, if the right child does not exist itself, we cannot directly push the value into the queue, right? It will throw an error. Rather, we check that whether this particular node or this particular subtree is present or not. If it is not present, then don't push anything. If it is present, then directly push that particular node into the queue. Because we write a rightmost node to be processed first at the next level. Now at step 4, which is the final output, then after the while loop ends, we return the list, the value which is basically stored in the list, we return it, right? Whatever it is stored. And this list contains one node per level, and it is the rightmost visible node, and it is from the top to bottom order. Because we process the tree level by level, rightmost first, and capture it from top to bottom. That's why our resultant vector or the array or the list has a required output. I hope you understood the approach. Approach is nothing much complex. It is straightforward, what we discussed earlier, and nothing much. Let's move to the next slide. The code is the exact copy of the approach we discussed. Let's understand it line by line. So first we check for the base case. If the root is not present, we just return the empty list. Otherwise, we declare a list and queue. And we we put the first node of the tree into the queue so that we could traverse the queue. Otherwise, we won't be able to do it, right? So while queue is there or while queue is not empty, we take the length for each level. And for this particular length, we iterate, we pop the node, we check if I equals to 0. Of course, if it is equals to 0, we append the value into the node. Then we check for the right. If right exists, push the right. If left exists, push the left. And when the complete traversal is done, we just return the result. Now, it might seem to you that since you're traversing the queue, it is off, and then you're traversing for I, it's again off W, okay, but it's not. It's only one single traversal because you are just checking the length of the queue and you're iterating from left to right. Again, you're checking the node from left to right. Fine. That's why the time complexity comes out to be O of M and space complexity is O of H. Why H? Because suppose this is a tree, okay, You have stored how many nodes? 1, 2, 3, 4. And what we call this particular thing? We call this height of a tree, right? What is the height of the tree? Height of the tree is 1, 2, 3, 4, right? We will say it is 4. That's why the or the space complexity for the resultant list is O of H. Okay. I hope you understood the code explanation. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. Let me draw this tree. Okay, so I have drawn this tree. Now, what would be the answer for this particular tree? It will be 1, 3, 7, 11, and 6. Correct? Yeah. Now let's do the dry run. So I have bought the code also here for your understanding. Okay. So let's start. First, we check if the root is not none. So it is not none, right? So we will keep on going. Let this be the queue. And initially we pushed root, right? So what is root? Root is 1. Root is 1. Great. Now, while queue is not empty, we take this size, the level, or let me write it as size. Fine. Let me write it here. So size for this particular level is 1. Okay. So it will go from 0 to 1, right? We pop the node in the node variable, which is 1. If I equals to 0, of course I equals to 0, we append it into the result. That is with our resultant array. And we check if the node right is there or not. It is there. So we push right, which is 3. Then we check if left is there or not. It is there, right? So we push 2. Since this is pop, we will remove it. Great. Now we came back. Now what is the size of the new cube? It is 2, right? It is, and then this will go from 0 to 1, 0 to 2, right? This particular range. We pop the pop left. We do pop left. So we pop 3. If we check if I equals to 0, yes, it is equals to 0 right now. So we append 3 into our list. Correct? We are in this particular level now. Then we check for that if the this particular has the root right or not. It has, right? It has 7 in this case. So what you do? You put it here. Then we check for the left. We have left, which is 10. We put it here. Great. Now we go for the. This is done. Now the range is from 0 to 2, right? So it will go from 0, comma 1, correct? Now we will pop 2, but I right now is 1. I has incremented to 1. Let me write 1. I value also here. Okay, so you cannot do anything and you cannot append anything. So you check for the node right. Does it have right? Yes, it has. It has 5. Does it has node left? Yes, it has. It has. It is 8. So put those values here. Okay. After that, this particular range is done. The 0 to 1 iteration is completed. Now we come back here again. What's the length of the new queue? It's 4. Okay. Let me write it here only. Length is 4. Okay. So it will go from 0 to 3. And this is for, if I index it, it is 0, 1, 2, 3, right? So this is I here standing here. So I equals to 0, correct. So we append this particular value into our resultant answer. Then we check that does it has right node 7? It does not have anything. Does it has left? It does not have anything. So we have already popped it. Okay. Now when we come to the 10th, now I value has become from it was 0 previously. Now it has become 1. Correct. Now if it is 10, if I is 1 and it is 10, so I is not equals to 0. So this won't happen. Node right does it have node right? No, it does not. Does it has node left? It has, which is 11. So we'll put 11 into the queue. Okay, and this is already popped. Now I becomes 2. This is 5. So appending does not happen. We just take the right value. It does not have left. It does not have. So we just pop it. Nothing else. Now I becomes 3. When I becomes 3, we have 8, right? Let me clear this up. So we have 8, right? So if it is 8, then we will be putting 9 here and then 8 right and left, right? Let me clear this up and write it again. So we had 8 and 11, right? So for this particular 8, we have right node, which is 9. We have left node, which is 8. And this is done. Okay. Now I becomes 3, then again I comes to 0. And then the length for this particular level is 3. And I starting from 0 again. Okay. Now what happens? We took the size. Now we are in this case. What is the pop left value is done? I equals to 0, true. Result dot append node value. And what is the leftmost value? It was 11, right? So we add it here. When we move the head and we check, does 11 has right? It does not. Does it has left? It does not. So we just popped it. Then again, I became 1. I is not equals to 1 or 0, correct? We cannot append anything. Then node right. For the ninth node, we don't have anything in the right? Must node left, we have 6. We push it under the queue. We pop it. Then again, we come to 8. We pop it. For 8, do we have anything in the right? No. In the left? No. We have nothing. Okay. Then we are left with 6. We came back. We again checked what is the size. Size comes out to be 1. I is in 0. Because in this particular level, we have only one node. So if I equals to 0, we append this value, correct? And we pop it. Then we check for, does it has any left? No. Right? No. So this is done. And so Q becomes empty. So this case falsifies. So we come out of this loop and we return the result, which is this one, 137.11.6, and which is our correct output. I hope you understood this dry run. It was pretty easy and straightforward. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code. And if the BFS logic is not clear, that also. After that, do a dry run by yourself on 2-3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since we are familiar with the problem and the solution, let's move to the lead code and code the solution. Okay, let's start by writing the base case. If not root, if root is not present, we will just return an empty list. Otherwise, we will declare an empty list. We will declare a queue using dq, and we will initialize it with the root node. Okay, while queue is not empty, we will take the size of the level. Okay, length of the queue. We will iterate here for I in range level size. We pop out the node. Then we check if I equals to 0, we will append in the result the node value. Otherwise, we won't do anything. We'll check if node dot right exists. If it exists, we just push the value into the queue. If node left exists, append queue dot append node dot left. Great. And after the complete traversal is done, we just return the result. Now let's try submitting the sample base cases. Okay, sample test cases has been successfully passed. Let's finally submit it. Okay, we have successfully submitted our solution. The code of the problem is available in the GitHub repository. You can find the link in the description. Thank you, everyone.